In this video, we will investigate how the derivative affects the graph of a function. And there's really kind of two key properties. The first is the first derivative property. And what it tells us is that if the derivative is positive on an interval, the function will be increasing there. If the derivative is negative on an interval, the function will be decreasing there. So let's just go ahead and apply this to a nice simple example. Let's determine where the graph of f is increasing and decreasing. So essentially what we need to do is figure out where the derivative is positive and negative. But as you can imagine, first we determine that borderline case, where is the derivative 0, and then we think what happens in between or outside of those zeros. So differentiating with the power rule, f prime of x is equal to 4x cubed minus 12x squared. And what we would like to know is what are the values of x that make this equal to 0. That is, we're first going to locate the critical points. So both of these terms have a 4x in common, and when you pull that out, actually 4x squared in common, and when you pull out that 4x squared, what you're left over with is an x minus 3. So x is equal to 0, or x is equal to 3. So now we make a number line, and we think, okay, for f prime, we know it is equal to 0 when we plug in an input of 0, and we plug in an input of 3. And we want to think what happens in each of these given intervals. We can be from minus infinity to 0, 0 to 3, 3 to infinity. And for this first example, I'll write down more details than you may need to, but just to help see what's going on. So we have our three intervals. We're thinking minus infinity to 0, 0 to 3, and 3 to infinity. Since we know exactly where f prime is equal to 0, 0 and 3, if we are anywhere else, it is never 0. So if you concentrate on one of these intervals, f prime is going to be entirely positive or entirely negative. So we just need to check one point. So in this first interval, minus infinity to 0, we can check the point that's, say, minus 1. So if we plug minus 1 in, we'll have 4 times minus 1 squared times minus 1 minus 3. Now, I do not care what this value is in terms of a specific number. I just care whether it's positive or negative. So we have a positive times a negative. So f prime is going to be negative on that interval from minus infinity to 0. Similarly, from 0 to 3, if I plug in 1, we have 4 times 1 squared times 1 minus 3. A positive times a negative is negative. So on the interval from 0 to 3, f prime is negative. On 3 to infinity, let's say I plug in 4, and you can pick your favorite number. Typically, I recommend just pick the easiest thing to work with, so usually a whole number. We would have 4 times 4 squared, which is a positive, times 4 minus 3, which is also a positive. A positive times a positive is a positive, so f prime is positive on the interval from 3 to infinity. Now, this portion where we've written down some details, if the function is reasonable enough, which I think it is in this case, you can simply kind of talk your way through it and just indicate the negative, negative, positive. So what this tells us, our function will be increasing wherever f prime is positive. So 3 to infinity. Our function will be decreasing wherever f prime is negative. That would be minus infinity to 0 and 0 to 3. Now note, for this interval of increase, it's tempting to just write minus infinity to 3, and intuitively that gives you the idea. The reason I break it up into two parts is because at 0 the derivative is 0, and technically not negative. Now, similarly, we have the second derivative property. So if the second derivative is positive on an interval, that means f is concave up. And remember, concave up is the graph which is opening upward. So it looks like a smiley face. And if the second derivative is negative on an interval, then f is concave down. So that's thinking function whose graph is opening downward. So we think of this as being concave down, kind of a frowny face. Now let's apply this to our example. Let's determine where the graph of this function is concave up and concave down. So we have the first derivative. Now we need the second derivative. So term by term, we have 12x squared minus 24x. And what we would like to know, once again, is where is this thing equal to 0? And then if we see what happens away from those zeros, we'll find where the second derivative is positive or negative. So note, both terms have a 12x. When you pull that out, you're left with an x minus 2. So to ask where this is equal to 0 tells us x is 0 or x is 2. So we now make a number line, and we're thinking, what is the sign of the second derivative, between the zeros and outside of the zeros? So now let's just talk our way through it. If I think of plugging in an input just to the left of 0, so think something like maybe minus 1, you would have minus 12 times minus 3. A minus times a minus will make f double prime positive. If we plug in something between 0 and 2, like 1, we would have 12 times 1 is positive, times 1 minus 2 is negative. Positive times a negative is a negative. And on this third interval, going from 2 to infinity, if we plug in a number like 3, we would have 12 times 3 is positive, times 3 minus 2 is positive. Positive times a positive is a positive. And we now have all of the information that we need. Where that second derivative is positive, our function is concave up. So minus infinity to 0, along with 2 to infinity. And where that second derivative is negative, our function is concave downward. Now, the last thing we could ask here is, since we know intervals of increase, decrease, concave up, concave down, we should be able to give a rough sketch of the function. So let's go ahead and do that. And first, I'm going to find one other bit of information. So for our function, in order to sketch it maybe a bit more accurately, we might just ask, where is it equal to 0? What are the x-intercepts? So if we pull out an x cubed, which each term has, what we are left with is an x minus 4. So the x-intercepts would be 0 and 4. So 0 and 4. And I've indicated underneath the axes what's happening. We start off decreasing, and then after 3 we increase. We start off concave up, and then at 0 we switch to concave down, and then concave up again. Also note, because we go from decreasing to increasing at 3, there is going to be a local minimum that occurs there. So let's just kind of start to the left and just talk our way through this. And one thing I like to do is wherever I'm changing concavity, I like to draw kind of just a dashed line to help me see where that concavity changes. So in this case at 2 and at 0, but since I have the y-axis, I'm not going to worry about that. So I start off decreasing and concave up until I hit 0. At 0, I switch concavity, so I remain decreasing, concave down. So decreasing, concave down. And then at 2, I remain decreasing, but now I'm concave up. And then right at 3 is where I switch from decreasing to increasing. So I'm going to be increasing, concave up, and I hit that root we knew that we had at 4. So this gives us, a fairly accurate sketch of what the graph of f will look like. I say fairly accurate because we have no scale in the y direction, though we certainly could figure out what the function value is at 3 and do a bit better of a job.